linear time invariant system governed by a differential equation. That governing differential equation is given. It's a causal LTI system. Now, for finding the so the question is you have to find the Fourier. The system is given and an input signal is given. You have to find the output signal, the Fourier series representation of the output signal. And we need these properties. If you are giving e to the power j omega naught t as input to a linear time invariant system, let's say ht is the impulse response, what will be the output signal? Eigenfunction property of complex exponential. What is eigenfunction property?
H of omega naught into
It is h of
j omega
I
naught
am
t.
writing it as h of j omega into e to the power j omega naught t. It is a constant times the input signal. That is why it is called. That is why the complex exponentials are called the eigenfunctions of linear time invariant systems. Okay, and what is this h j omega naught? What is h j omega? It is this integral ht into e to the power minus j omega t dt. Anyway, this we will discuss about this later on. But here there is a method to find this impulse. This is called, what is this called? This has got a special name. I have explained. I remember I explained that for a low pass RC circuit, RC integrator. It is called the frequency response. I have demonstrated how why is it called a frequency. I have explained that why is it called frequency response and why that RC integrator is called a low pass filter. Okay. So if you are given the this a differential equation that governs the input and output of a linear time invariant system, you can find the frequency response. This is called the frequency response from this. Okay. If you are taking, this is the input output relation of that linear time invariant system. If you are taking xt as e to the power j omega t, what is yt? If xt is e to the power j omega t, what is yt? Using the eigenfunction property, is it h j omega into e to the power j omega t? Is it that?
Yes, sir.
That is the eigenfunction property. Then what is dyt by dt? If yt is this, what is the derivative? Look, this is a function of omega only. This is not a function of t.
J omega times.
It is
H of
s j omega into j omega times e to the power j omega t. Now, if you put these values here, will we get something like this? H j omega into j omega. Oh, sorry. If you put it here, you will get h j omega into j omega e to the power j omega t plus 4 e to the power j omega t e to the power j omega t. Xt and yt we know. If xt is e to the power j omega t, this is yt and this is the derivative of yt. I am putting these values in this differential equation. Is it?
Yes, sir.
Now can we find h j omega from this? Is it this?
So yt is also h of j omega times e raised to
Yes,
j omega.
yes, this is h of j omega times. Then only you will get this. Is it?
Yes.
So we know h of j omega. Now, what is the relation between the input, the Fourier series coefficients of at the input and the output of a system? If you are giving a periodic signal as input to a linear time invariant system, what about the output? Will it be periodic? Let's say the input signal is xt. What is the Fourier series representation? If the Fourier series coefficients are ak, is it minus infinity to infinity ak e to the power j k omega naught t? That is the Fourier series representation. Now, if we are giving this as the input to a linear time invariant system, what will be the output? What is the output corresponding to e to the power j k omega naught t? System is linear time invariant. If you are giving the kth harmonic as the input, what will be the output? Is it h of j k omega naught into e to the power j k omega naught t?
Yes, sir.
Now, if you give a linear combination of this, then what will be the output?
Summation AKH JK omega naught.
J k omega naught into e to the power j k omega naught t. That is the output. Now, what are the Fourier series coefficients of the output signal? Is it this?
Yes, sir.
ak into hjk omega naught t. So that is the property. We can write it like this. If you are giving xt, a periodic signal as the input to a linear time invariant system, and let's say output yt, if its Fourier series with respect to period, some period t naught is ak, then it's the Fourier series of this with respect to the same period, that is ak into hjk omega naught. Okay. Now we have found the value of hj, and we know the value of omega naught. What is the value of omega naught? Okay, now we have to consider the signal. What is the signal? Given signal xt is equal to minus infinity to infinity minus 1 to the power n delta t minus n. Is it a periodic signal? Is this a periodic signal?
Yes, sir.
What is the fundamental period?
The 2.
Is it this signal? At 0, you have an impulse of strength 1, and 1, you have an impulse of strength minus 1, and then this is the signal. Okay. Find the Fourier series coefficients. What are the Fourier series coefficients? Okay, let me explain this. So here 0, 1, this minus 1 is this. Remember, this is a period continuous time signal. It is not a discrete time signal. This is impulses. Okay, strength 1. Now, how to find the Fourier series coefficient of this signal? If you are given xt, what is ak? Is it this 1 upon t naught integration over t naught xt e to the power minus j k omega naught t? Is it that? That is the
Yes.
Fourier series analysis equation for continuous time signal. Now, what is omega naught here? 2 pi by?
T naught.
What is t naught? 2 pi by 2, isn't it? T naught is 2 in this case. Is it? This is a periodic signal with period 2. This is 0, 1, 2, 3 like that. Okay. Now, if we find the Fourier series coefficient, this is integration over one period. And if you consider any one period, how many impulses will be there in one period? How many impulses?
2.
There will be 2 impulses. Okay. Suppose I am considering one period, let's say something like this, length 2. There will be 2 impulses. Then what is this expression? It is 1 by 2 into integral. But how many impulses will be there? What is this integral? Multiply with these two. Is it this integral? I am taking, for example, I am taking this integral from minus 0.5 to 0.5, 1.5. Okay, that is an interval of length 2, that is one period of that signal. Then what is the expression? Can we write this as delta t plus delta t minus delta t minus 1 into e to the power minus j k omega naught t. Is it that?
Yes, sir.
Can we simplify this? 1 by 2 into what? What is the first one?
E minus
This is non-zero
function
only when
itself.
t is equal to 0. So is it 1 minus what? Minus
E to the power minus jk omega.
jk omega naught. These are the values of ak. Okay. Now use this property. This one, you will find the Fourier series coefficients of the output signal. You can solve it. Okay. Eighth question is similar. Only difference is that it is a discrete time system. It is a discrete time system. Okay, that is an interesting question. Let me explain that. The the eigenfunction property of discrete time system that is valid for the LTI systems, that is valid for discrete time systems also. I'm writing that property. If e to the power j, let's say j omega naught n, if it is a periodic signal where omega naught, I am writing it as 2 pi by n. If you consider a periodic discrete time periodic signal with period capital N, if you are giving it as the input to a linear time invariant system, the output is also, it is e to the power j omega n times a constant, and that constant I am writing, it is okay. There is a, in the case of continuous time systems, I have written it as j omega, but here I am writing it as e to the power j omega naught. We'll discuss that after the midterm. Why is it written as e to the power j omega naught? So the property is same. So here h e to the power j omega is okay. And from minus infinity to infinity. It is similar to continuous time system. Continuous time system h j omega is integral minus infinity to infinity h t to the power minus j omega t. So here, instead of that integration, it is a summation. That is the only difference. Okay. Now the other properties are also same. If you consider, if you give xn as the input to a linear time invariant system and output is yn, and if this is a periodic signal, the output is also periodic with the same period. And okay, so xn inter, if these are ak Fourier series coefficients ak and these are bk, then we can write ak as sorry, it is not minus infinity to infinity, it is summation over one period. Sorry, not ak, it is xn. And yn is that's also similar to continuous time Fourier series representation. Only difference is that here it is summation over one period. Okay. Okay, now let us find the Fourier series coefficients of the signal xn. What is the Fourier series coefficients of xn? What is xn? What are the Fourier series coefficients? This is an impulse train, isn't it? There are impulses 0, 4. What are the Fourier series coefficients? If you consider the Fourier series with respect to period 4, what are the Fourier series coefficients? Impulse train, is it 1 by 4? Is it 1 by 4?
Yes, sir.
It is 1 by 4. It is constant for, if you denote it by ak, then ak is 1 by 4 for all k. Okay. So we know that the Fourier, now we know the Fourier series coefficients of the input signal. Now it is given that if you are giving this as the input signal, the output is yn is cos 5 pi by 2n plus pi by 4. This is given. Now what is this yn? What are the Fourier series coefficients of yn in terms of xn? If you are giving this as input to a linear time invariant system, will the output be is it this? Same as the similar to the this continuous time system, the previous problem that we discussed.